of biocomposites. Please be seated. We'll start the session soon.
Well, so it's okay. Uh, some people is missing.
Lunch session or something you want to have more questions. Basically, he's only have 11, but I don't think that he's away from somewhere. He said he's very close, he's very good, he's good for me. So, we have
Okay, can start? Okay, so polymer processing, biocompository processing. It's not working. I'm sorry because of the noise with my beard. The beard is new, it's since 3 years. First it was because my daughter asked me for Christmas, but so I keep it fairly. That's okay? Thank you. First, what is important to understand is that during processing, of course, we start from a material to obtain a final product, but starting from the same material, we can obtain different properties of the final products depending on the processing technique which is used. The properties of the polymer product depend, of course, on the chemical nature, the chemical structure of the polymer, but also some other properties like the molecular weight distribution, and so on. It depends also on the presence of additives. So additives are often used to improve or to change some properties. So it can be, for example, lubricant. So the objective of lubricant, of course, is to use a material that will melt at a temperature which is lower than the processing temperature in order to form a liquid film at the interface between the material and the mold to facilitate the demolding of the material. So some other additives can be used, like, for example, plasticizer. Do you know what is the objective of using a plasticizer? You will tell me to plasticize? No? So plasticizer is an additive that should consist in a low molecular weight molecule in order to diffuse easily in the polymeric network. And the other condition is to have good interactions with the polymers that we want to plasticize. So the objective, of course, is to homogeneously distribute this plasticizer molecule in the macromolecular network in order to limit the interactions between the macromolecule. And so it results in a less cohesive material, and at the end, the glass transition temperature and the melting point, if the polymer is semi-crystalline, are reduced. So one polymer which is classically used in the form of a plasticized polymer is PVC, polyvinyl chloride, and we have totally different properties because, for example, the TG of PVC is around 80 degrees, so meaning that at room temperature it's a stiff polymer, but when adding enough plasticizer, we can decrease the TG, the glass transition temperature, below room temperature. So even if room temperature is maybe higher than in Kerala than in France. And so we have now flexible polymer. We can use also stabilizer in order to improve the stability of the polymer, so against UV light or thermal degradation and so on. Flame retardant, reinforcing agent, this is what we discussed previously. Filler, so remember that filler is also a solid particle which is added to the material, but usually it's not in the form of a fiber. It's a more or less spherical particle, or it can be platelet-like particles, and the objective is mainly to reduce the price of the material. So different additives can be used, and of course this additive will impact the properties of the final material. But the processing conditions are also important. So there are typically two families of polymers that we already discussed, thermoplastic and thermoset polymer. You can see in this table the characteristic of each family and the resulting properties that can impact the processing of the material. So thermoplastic material or thermoplastic polymers consist of linear or branch macromolecules. And one important consequence is that this material can be fully amorphous or it can be semi-crystalline. So it depends on the nature of the polymer and so on. So there are different parameters that can impact the ability of the polymer to crystallize. But even if the polymer crystallizes, it is always only semi-crystalline. There are two reasons for this. The first one, we are considering very long molecules, macromolecules. And of course, we have some entanglements between these macromolecules. During crystallization, we have a diffusion of these macromolecules during cooling in order to organize regularly to form the crystalline domains. Because of these entanglements between these macromolecules, the diffusion can be limited, and the organization of the macromolecule can be limited. This is one reason for which polymers are always semi-crystalline. Another reason is that during crystallization, the viscosity of the medium is increasing. And of course, the diffusion of the macromolecules becomes more difficult, meaning that for each polymer, there is a maximum degree of crystallization. And it depends on different parameters. For one polymer which is well known to have a high degree of crystallinity is Teflon. Tetrafluoroethylene. No, Teflon. Maybe it's easier, which has a degree of crystallinity of about 90%. I spoke about PVC. PVC is a semi-crystalline polymer, but the degree of crystallinity is very low, so it's around 10%. So anyway, this thermoplastic polymer can be amorphous or semi-crystalline. Now regarding thermoset polymer, we are considering cross-link macromolecules. So meaning that there are some covalent bonds between this macromolecule, meaning that the molecular weight can be considered as very high. It's a 3D polymer. In this case, you can imagine that the diffusion of the macromolecules, when cooling the material, the diffusion is impossible, meaning that these materials cannot crystallize and they are always amorphous. Now, in the case of thermoplastic polymers, the lateral cohesion or the intermolecular interaction are due to what is called secondary links. Secondary links means van der Waals interactions, of course, which are universal, that can be found in any material, but also other interactions, which are stronger, and that depends on the chemical structure of the polymer. So it can be hydrogen bonds, for example, or ionic interaction, and so on. Secondary links is maybe not the right denomination, because in some cases, these secondary interactions are stronger than the covalent bonds. Do you have any example of such a polymer? Cellulose. Can you melt cellulose? No. When you increase the temperature, we have some strong hydrogen bonds between the macromolecules, meaning that it's a thermoplastic, but the secondary links are very strong. It's a highly cohesive material. And when heating cellulose, instead of separating the macromolecule, the polymer can be degraded, meaning that some covalent bonds are cut. Meaning that in this case, these secondary links are stronger than covalent bonds. But generally, one property that results from this characteristic here is that thermoplastic are sensitive to heat and to solvents. So heat, meaning that when heating the polymer, it changes from a stiff behavior that corresponds to the glassy state to a softer material, which is a rubbery state, and then the material can flow. Sensitive to solvents. So solvents are molecules which are equivalent to plasticizer. Short molecules with a good affinity with the polymer, but in this case, the solid content or the polymer content is much lower, meaning that the macromolecules are completely separate and they are dissolved. Now for a thermoset polymer, the lateral cohesion results from covalent links, cross-linking, meaning that the material is infusible. When increasing the temperature, you cannot melt the material, you cannot obtain a liquid, and it is insoluble. When mixing a thermoset polymer with a solvent, the material can swell, but it cannot dissolve. And this swelling behavior can be used to determine the cross-linking density of cross-linked polymers. Now, from processing point of view, thermoplastic can melt or can flow when increasing temperature, meaning that it's quite easy to process this material because you just have to heat to increase the temperature, change the viscosity of the material, you can obtain a liquid, and this liquid can be shaped in any form using different processing technique, and then this shape has to be fixed by cooling the material. And this process is thermoreversible, meaning that after obtaining a product, the material can be processed again. So meaning that you can increase the temperature, give a different shape to the material, and by cooling this shape. In fact, it's not possible to make this process several times because during processing, shear force are applied to the material and temperature is also applied to the temperature is increased. And this process progressively degrades the polymer, meaning that the molecular weight decreases. So it means that this kind of thermoreversibility is possible, but only a few times. Just a comment here, I mentioned melting or flow. In fact, melting is used even for amorphous polymers. Even if you know that melting consists in the transition from a crystal to a liquid. For amorphous polymers, there is no crystal, no crystallinity. But you know also that polymers are viscoelastic material, meaning that they have a behavior which is between an elastic solid and a viscous liquid. And depending on the temperature, the viscous or elastic behavior can be more or less significant. And we call melting point or melting temperature the temperature for which the viscous behavior becomes more important than the elastic behavior of the polymer. One important thing, thermoreversibility. It's not recyclability. It makes a difference. So in the case of thermoset, the processing needs to be performed before heating. So it means that for processing a thermoset polymer, it's necessary to mix a monomer or a prepolymer with a curing agent that will promote the cross-linking of the material. And for this, it's necessary to heat the material because there is a chemical reaction. So you can understand that, of course, the processing cycle will be longer and the industrial use of thermoset is limited compared to thermoplastic polymers. But high-performance material can be used, and these materials are not thermoreversible. After shipping the product, you cannot reprocess this material, but it is recyclable. For example, you can grind this thermoset polymer and use the resulting powder as a filler to add to another thermoplastic or thermoset polymer. So it's a kind of recyclability, but it's not thermoreversibility. So maybe you had class on polymers, and you will tell me there is one family of polymer which is missing. Yes? No? Elastomers, yes. It's not here. Why? What is an elastomer? You start, you have to continue.
Like the arrangement of unsaturated bonds.
Yes, also, not from a chemical point of view. The characteristic of an elastomer is that it is easy to deform, okay? And the deformation is reversible. Why is it easy to deform? Because it is easy to break the intermolecular interactions, meaning that this material is in the rubbery state, meaning that the glass transition temperature is below room temperature, which is the case for natural rubber with a TG around minus 60 degrees Celsius. But also, when you deform this rubbery material, you have an irreversible deformation. And to avoid this, it's necessary to cross-link this rubber, and a cross-link rubber is an elastomer. Okay? But, so meaning that finally we have a thermoset polymer. In terms of processing, it's exactly the same thing. There is a difference between elastomer and thermoset. Usually, in the case of thermoset polymers, there is one cross-link point every 10 monomers, more or less. In the case of elastomer, it's only every 100, more or less, monomer, because the objective is not to have stiff material, but to have a reversible deformation. Okay, so meaning that for me, elastomers are included in thermoset polymers. So polymer processing is an operation that consists in shaping the material resulting from the synthesis. So it can be in the form of a powder, granules, it can be a liquid, mainly for thermoset, granules or pellets mainly for thermoplastic polymers, to give it a geometry of a finished object corresponding to the usage properties. Regardless of the processing technique that is used, there are different steps, which are here. The first one is plasticization. So it's a thermal processing, so it means that it's necessary to heat the material to pass from a solid to a liquid state. Then the shaping of the material, which is a mechanical process that results from flow, which is induced by applying pressure. or force. And then shape conservation. And for this shape conservation step, there is a difference between thermoset and thermoplastic polymers. For thermoset, it's heating. It's necessary to heat, for example, the mold to promote the chemical reaction, the polymerization, and the cross-linking of the polymer. And in the case of thermoplastic polymer, it's a cooling step. So it's necessary to decrease the temperature in order to freeze or to fix the shape of the material in the mold. So on this slide, you can see the state of the polymer at the beginning of the process. So depending on the process, different stiffness are necessary. And you can see here the evolution of the modulus of a polymer as a function on a logarithmic scale, as a function of temperature. So you probably know this kind of curve. So at low temperature, the modulus of the polymer is around 1 gigapascal for any polymer. And by increasing the temperature, the material passes from a glassy state to a rubbery state. And so we have a sharp drop in the mechanical properties, in the stiffness of the material, down to about 1 megapascal when considering an amorphous polymer, so it's higher for a semicrystalline polymer. This is associated to the glass transition, but it's not a transition. I don't know if you know the difference between a transition and a relaxation process. A transition is a passage from one state to another one, from the glassy state to the rubbery state, from the crystal to the liquid. It is a fusion, from the liquid to the crystal, crystallization, and so on. Relaxation is a process that corresponds to a difference in the molecular mobility of the macromolecules. Of course, glass transition is associated to a relaxation process. Because when the material goes from the glassy state to the rubbery state, the molecular mobility is different. Meaning that, of course, there is a relaxation process which is associated to this transition. The same for melting and for crystallization. But there are some relaxation processes which are not associated to transition. So it is going out of this explanation on processing, but we have to keep this in mind. You can determine a glass transition temperature using differential scanning calorimetry, but not this kind of measurement, because it's not a transition, it's a relaxation. So I will not detail all this processing technique, but of course, the evolution of the modulus is linked to the evolution of the viscosity of the material. And depending on the processing technique, it's necessary to have different viscosities. This is what I mentioned previously, polymer melt, which is a term equally applicable to semicrystalline and amorphous polymers. Even in the case of amorphous polymers, there is no fusion or melting. By convention, it is used when the polymer is in the condensate state, so it's not dissolved, and the viscous phenomena are preponderant over the elastic phenomena. So viscosity is, of course, an important parameter for processing. You probably know that a liquid is not defined by its form or its shape, but it is defined by the rate at which it can be deformed. And the consequence of this is that there is a linear relationship between the stress, which is applied to the material, and the shear rate, which is here. So gamma corresponds to the deformation of the strain, and the The parameters that rely these two terms is the viscosity of the material. We can observe different behavior when plotting the evolution of the stress as a function, so the stress as a function of the shear rate. We can have what is called a Newtonian liquid. You can see that the slope of this curve corresponds to the viscosity. For a Newtonian liquid, the viscosity is constant and it doesn't depend on the shear rate which is applied to the material. Now we can have a shear thickening liquid. You can see that in this case, when increasing the shear rate, the slope of the curve increases, meaning that the viscosity increases. And at the opposite, we can have a shear thinning behavior, meaning that when increasing the shear rate, the slope decreases, then the viscosity of the polymer decreases. So what do you think about polymer melts? They are Newtonian fluid, shear thinning liquids, or shear thickening liquids. Do we have any idea? Yes, so you are expert. It's a shear thickening. Shear thinning. Yes, exactly. It's a shear thinning behavior. The reason for this is that, so we are considering long macromolecule in the liquid state, meaning that these molecules are flexible, and they are in the form of what is called random coils. And when applying a shear stress to this material, we can, in some condition at least, have an orientation of the macromolecule. And because of this orientation, the viscosity decreases, because we can also have some disentanglement between the macromolecules. And we can have also what is called a Bingham body with different behavior. So for Bingham body, you can see that it's necessary to apply threshold or critical concentration in order to observe the flow of the polymer, or of the material, sorry, of the liquid. So again, I have an expert here. Do you know any Bingham body? Yes, for example. Toothpaste also, because when you take the tube, it doesn't flow. It's necessary to exert a force on the tube to obtain the flow of the liquid. So we have this different behavior, but what is important to remember is that in the case of polymer melt, we have a shear thinning effect. This is what is reported here. You have the evolution of the viscosity as a function of the shear rate. And at the beginning, I mean for low shear rate, we have what is called the Newtonian region, meaning that the viscosity is constant. And then from a critical shear rate value, we observe this shear thinning behavior. So we have to imagine these random coils. And it's necessary to compare two characteristic time. The first one is called the relaxation time. So it's the time which is necessary to the macromolecule to move. You try to deform it. If it can easily recover the equilibrium position, in this case, the relaxation time is short. If not, of course, it means that the material will remain deformed. It's necessary to compare this relaxation time that depends on temperature, of course, and the time which is characteristic of the experiment. This time is related to the shear rate. If the shear rate is slow, it means that the experimental time is long. if the shear rate is high, the experimental time is short. And so it's necessary to compare these two times. At low shear rate, the relaxation time, so the characteristic of the polymer is low compared to the experimental time, meaning that at any time the macromolecule is in its equilibrium state in the form of a random coil, and when increasing the shear rate, we can have a permanent orientation of the macromolecule and then a decrease in the viscosity of the matter. What we should observe is a second stabilization for higher shear rate, because when the macromolecules are completely oriented, the viscosity should not change anymore. But we cannot observe this second plateau. The reason for this is that before that, we have a phenomenon which is called melt fracture. Because, of course, these macromolecules are very long, we have some entanglements, and when applying high shear rate, we can break the macromolecule. This is what is called melt fracture. And so we cannot reach this high shear rate, this second plateau, because of this phenomenon. So this is the evolution of the stress as a function of the shear rate. In fact, it is the same curve as this one, where we can observe the Newtonian behavior at the beginning, then the shear thinning behavior, and this second plateau that cannot be observed experimentally. So different laws have been proposed to describe this behavior. The most used is called the power law. So it is this law where you can see that the viscosity is linked to the shear rate, and there are two parameters, M, which is the flow consistency index, and N, which is the flow behavior index. This parameter is between 0 and 1. It is 1 for a Newtonian fluid, because you can see that in this case, there is no dependency of the viscosity on the shear rate. So this equation or this law is broadly used, but it only represents the behavior of the material in the shear thinning range, which is what is here. It doesn't account on the Newtonian plateau. It's not really a problem, because for any processing method, the shear rate will be high enough to be in this shear thinning range. But sometimes it can be useful to have the total description of the curve, and so different equations can be used. Maybe the most used equation is Karo-Yasuda law. Pierre Caro is professor at Polytechnique Montreal. He was my supervisor for the master. It was a long time ago. And he proposed this equation that describes the whole evolution. So eta is the viscosity. Eta 0 is the viscosity for low shear rate. Eta infinite is the viscosity for very long shear rate. We cannot determine this parameter, meaning that it's an adjustable parameter. And you can see that there is another parameter, lambda, which is a time constant that describes the mobility of the macromolecule. I'm just looking, I have no time to describe this more, but anyway, in this case, you can see that, so you have experimental data here, and this is the description of the power law, and when using this model with two adjustable parameters, we have a good fit of the behavior on the whole shear rate range. So now how can we determine the viscosity of the material? There is one parameter or one technique which is used, which is a normalized, it's a standard, which is called the melt flow index. This is very easy to determine, and then it is broadly used if you need to buy a thermoplastic in the form of pellets. So you have different information. One is the average molecular weight. Usually it's the average molecular weight by weight. But you have the polydispersity index. You have also this melt flow index. It is just an indication of the viscosity or the fluidity of the material. This is the principle of the measurement. It is a measurement of the mass of extrude polymer during 10 minutes at a constant temperature, 190 or 230 degrees Celsius. So it depends on the polymer. So it can be found in the standard. For example, in the case of polyethylene, it's 190. For polystyrene, it's 230. Through a cylindrical die, which is here, which has a diameter of 2.2 millimeter, under the action of a mass, which is here, of 2.160 kilograms. So a barrel is used here. It is heat at 190 or 230 degrees. The polymer is melt in this barrel. There is a piston that pushes the polymer that is extruded through this die. And then we can recover the extrude polymer. And you can see that the melt flow index corresponds to the mass of polymer which is extruded during 10 minutes. So usually the measurement is performed during only 1 minute, and so the result is multiplied by 10 to obtain this MFI. So this value is indicative of the fluidity of the material, even if shear rate values which are accessible by this technique is very far from what is obtained during processing, for example, extrusion or injection. But it's just an indication. And depending on the value of this melt flow index, the polymer is intended to different processing technique. Injection molding, extrusion, and so on. You have some indication here. When the melt flow index, so in grams per 10 minutes, is around 10, this kind of grade is called generic grade. It can be used for different processing technique. Now, when increasing the fluidity, so when decreasing the viscosity, usually these polymers are used for injection molding, and for lower melt flow index values, it corresponds to what's called extrusion grades. So the problem is that you have one example here of, this is for a nylon, two nylons with different melt flow index values. And you can see the complete behavior over a broad range of shear rate. It's a different behavior. Imagine that the condition corresponding to the melt flow index measurement correspond to this shear rate. It means that we have the same melt flow index for the two polymers, but you can see that the rheological behavior is different. So, meaning that you have to be careful with this parameter. It's just an indication of the fluidity of the material. So, maybe I don't know if I will describe this too much. This is a capillary rheometry, which is very similar to the measurement of the melt flow index, except that in this case, the speed of the piston can be changed. So it means that we can change the value of the shear rate which is applied to the material, meaning that we can have a complete description of the rheological behavior. So it's a more classical, of course it's a longer measurement, but we have more information. So now I will come to the processing techniques. I have had this slide because it seems that this afternoon you will use this, which is solution casting or casting evaporation. So it's very easy to perform. For this, it's necessary to use a solvent. So the polymer is dissolved in a solvent. So if it's a water-soluble solvent, water-soluble polymer, of course, water is used. but so some other solvent can be used for, so it's better to use water, but we can use other solvent. So the polymer is dissolved, and then the natural fibers are added in the dry state or in the form of a dispersion. So for this, it's necessary to have a relatively stable dispersion of the natural fibers in the same liquid as the solvent for the polymer. So this is mixed, and then this mixture is cast in a mold, and then it is evaporated like a paint to obtain a solid composite material, composite film. So you can see that the process is very easy and the material to be used is relatively limited. What is the main drawback of this processing technique? Sorry? Homogeneity can be a problem, but imagine that the polymer is well dissolved and the fiber are well dispersed in the liquid. Homogeneity is not a problem in this case. Now, the main problem, yes, you have a high amount of liquid to remove, meaning that it's a long process. Another problem that can be associated to this process is sedimentation. If the process is long, if the density of the fiber is higher than the density of the polymer, you can have a sedimentation of the fiber during liquid evaporation. Anyway, it's very simple to use. Another technique, which is also quite easy to perform, is compression molding. This process is used mainly for thermoset polymers. By applying heat and pressure, a measured amount of the powder, of the material, in the form of a powder, granules or pellets, is fed into the mold cavity. It allows the material to soften, and the pressure allows to fill the cavity of the mold, which is here, to fill the cavity. Then the material is cured, so it is cross-linked. It actually causes the polymer to soften and then harden into a highly cross-linked and network structure. This process is primarily used for thermosetting materials and is of limited use for thermoplastic. And one important drawback in this case is the absence of homogenization. So it's a simple process which is derived from what is done, for example, for metals. To have some homogenization of the material, it's possible to use what is called transfer molding. In this case, you can see that the mold is formed of three parts. The part which is at the middle is called the transfer pot. And the material is put in this part at the beginning of the process. It melts here, and then when closing the mold, when closing the press, the material is injected into the cavity of the mold. This technique is mainly used when considering thick objects, higher than 4 millimeters, because, of course, you imagine with the previous the previous technique, cross-linking occurs by heating the material by conduction. And of course, you know that polymers are poorly conductive of heat, meaning that the cross-linking process starts at the surface of the product. If the material is too thick, you have a gradient of cross-linking, which is not the case here. Variable thickness can be used, and of course there is a mold with multiple cavities that can be used. So just for the principles that I briefly explained, this process consisting in melting out of the mold in what is called a transfer pot, the quantity of molding material which is necessary for a single molding, and then it is transferred under pressure to the cavity of the mold. Now for thermoplastic polymer, which are broadly used, of course. Maybe the most important technique is extrusion. Extrusion can be defined as the fact of shaping a material by forcing this material through a die. It consists in forcing a previously heat softened plastic material through a shaping orifice, which is called a die, by means of pressure. So you have what is called the hopper here, in which you can insert the thermoplastic polymer, which is usually in the form of pellets. You have here a barrel, which is heat, in order to melt the polymer. And you have here what is called a reciprocating screw that is used to transport the material, which is progressively melt. So it is melt by, of course, the barrel, by conduction, but an important source of energy, which is used to melt the material, about 80%, is the shear stress, which is applied, which generates some heat. And so at the end, you can have a die with different form in order to obtain a finished product. So I will not describe all these things, but another extrusion process use two screws, instead of only one. So it is called twin screw extrusion. And in this case, it is used mainly for what is called compounding. So it means that granules are used, polymer granules, with different additives that can be, for example, natural fibers. And both materials are extruded at the same time. And a twin screw extruder is used to facilitate the mixing. And at the end, a material is used that consists in the blend or the mixture of these different components that can be pelletized and then used for another processing technique. I have a short video that shows this. It's working, perfect. You can see two, so it can be two polymers, for example, or a polymer and some filler or fibers, which are used. You can see that there is a given profile of the screw with some zones that are used just for the transportation of the polymer, some which are called kneading zone that promote the mixing of the different components and so on. So the design of the screw is very important to have an efficient mixing process. We should obtain green color, but not when mixing yellow and blue, but not, because it's not visible. Oops, sorry, I think I missed maybe one. No. Yes. So this is a specific family of biocomposite, which is called wood plastic composites. So it consists of mainly 3 or 4 components, mainly 3, let's say. The matrix, which is generally a polyolefin, so it can be polyethylene, can be polypropylene, but it can be also PVC, and which is mixed with wood flour, up to 60%, so it's a quite high content. And a lubricant is used just to facilitate the mixing of the two materials. And as mentioned previously, a compatibilizer is necessary, and generally a copolymer of anhydride maleic anhydride, and polypropylene is used with 2 to 6% of anhydride maleic moieties. So, just for some information on the lubricant, it can be an internal or external lubricant. So metal stearates, such as a zinc stearate, can be used. this kind of wax can be used, and the objective is to improve the quality of the surface and some properties also. I didn't remember that I had this video. Sorry, but these are some examples of use of wood plastic. Ah, yes, 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 I remember. Yeah, yeah. Yes, so the first step is, in this case, recycled PET is used. So this is the first step, which is the washing of this recycled polymer. Which is not really part of the processing step, because when virgin polymer is used, this step is missing. So the second step is, you can read, the production of the wood powder. This kind of material, which is mainly used for construction, is quite popular in US, but not too much in Europe, where we prefer plain wood, in fact. So the next step is the mixing of this wood flour with the matrix and pelletizing. So this is typically a twin screw extrusion process, and then it can be extruded using a single screw extrusion process with a die that has the shape of the final product. So you can see that the material is, the polymer is becoming brown, of course, because of the wood powder. So this color comes from the presence of lignin, because when considering pure cellulose, it is white, but when lignin is present, it's darker. Okay, and it can be also it can also result from some degradation. Because in this case, I think PET was used, so it can be extruded at quite high temperature, meaning that some degradation can be observed. And so this is the final step, the extrusion of the final product using a single screw extruder. And so this can be used in this case, of course, for a terrace or other. So it's good because there is no, let's say, it's more resistant to weatherability, but the problem is that when it is hot, maybe it's not good for Kerala, when it is hot, you can burn your feet. So this is the final step. Well, I think it's the end. Okay. So this is just some data about the wood plastic composite market with some predicted evolution. So it is supposed to increase, but I think that it is the case for any product, because you know that the population is increasing and the demand of the population is increasing, meaning that the demand of material is increasing. So this is by application, so just to show you that building and construction is an important market for this. So another technique that can be used to process thermoplastic polymer is injection molding. You can see that it looks similar to extrusion. The main difference is that in this case, the screw not only rotate, but it can translate. But we have also a hopper, a barrel to melt the material. So this material is melted progressively and it accumulates at the end of the barrel. So the entry of the mold is closed at the beginning, and so meaning that the screw is going in this direction. And when enough material is present, when enough material is melted, the screw translates and the gate of the mold is open to inject the molten polymer into the cavity of the mold. So it consists in injecting the molten polymer into a cooled closed mold, cooled because it's a thermoplastic, where it's solidified to give the product, the mold open and the product is released. So the main difference with extrusion is that the screw does not only rotate, but it reciprocates to and for, thereby injecting the melt in the mold. So this is a detail. So you have here the different steps in the injection molding process. So the mold and the valve are closed at the beginning. The polymer melts in the injection unit, and the screw accumulates a shot of melt. Then the valve opens and the screw forces the melt through the nozzle into the mold. Then there is a hold on stage, so meaning that the pressure is applied to the material. I don't have time for this, but it's just to limit the shrinkage of the polymer, because the specific volume of a polymer depends on the temperature, and when cooling a polymer, the specific volume decreases, meaning that we can have a difference in volume. When the mold is cooled, the press is opened and molding removed by ejector pins. So this is another technique which is used also for thermoplastic, but which is very specific, because usually to process thermoplastic material, a cold mold is used. In this case, for this technique, which is called rotomolding, the mold is at high temperature. So it's a process which is competitive with blowing that you mentioned previously for large volume but less suitable for large series and small thin wall article. It's a thermoplastic which is used, but it is used in the form of a fine powder. It's not pellets. It is deposited in a closed heat mold, able to be put in double rotation around two orthogonal axes. This is a powder. The mold is closed. The powder is distributed over the inner surface of the heat mold, and it gels. Fixing of the gel part by cooling and obtaining a hollow body close by demolding. And of course, the weight of the molding is equal to that of the powder which is used. So you have the different step. The powder, which is added into the open mold, which is closed, it is rotating in two directions, and the mold is hot, meaning that it melts locally the polymer. Then it is cooled in order to fix the mold polymer, and then it is removed. So these are some, I have 10 minutes more, it's okay? Okay. I will go fast for this. Some specific processing technique which are only used for composite, because the previous technique can be used for thermoplastic or thermoset polymers. Production of SMC sheets. SMC is for sheet molding compound. In this case, you can see that fibers are used. So in this case, it's glass fibers in the form of what is called a roving. And these fibers are shot to obtain shorter fibers, and they fall on a conveyor belt on which a layer of resin and the different additives are put. So this short fiber fall on this resin, and then a second layer of the resin and additives with some impregnation system. And then this material is obtained in the form of sheet that can be, for example, used for compression molding. BMC is for bulk molding compound. So it's a similar process, except that in this case, all the material or the other additives, the resin and the fibers are mixed in a container, which is rotating. And in this case, usually, and because of this rotation, the fibers are shorter. I don't know if I describe all of these things. Maybe it's not necessary, but it's the most common additives which are used for SMC or BMC formulation. On layup, it was mentioned previously, so it's a quite simple method, but which can be used for a large part. Usually, a gel coat is applied in the mold. So this gel coat is a small layer or a thin layer of the pure matrix. And then the reinforcement in the form of mats, for example, is deposited. The resin is added, and it is homogenized on the surface of the mold. And then the material is cured at room temperature. So you can see that the method is quite simple. No heat is involved, but of course it's a quite long process. And spray up is very similar, except that in this case it's more, let's say, automatic, because both the resin and additives and the fibers are sprayed with a gun. And filament winding is also a specific processing technique which is used for composites. So winding filaments under tension are impregnated in a bath that contains the resin, and then they are wound onto a rotating mandrel. The mandrel rotates around the spindle and move horizontally in line with the axis of the rotating mandrel, laying down fibers in the desired pattern or angle. And when the mandrel is completely covered, the resin can be cured. You can understand that in this case, of course, the fiber content is very high. So it's usually more than 80%. Pultrusion, which are also similar. So pultrusion comes from pull and extrusion. So it means that there are some similitude with extrusion. Again, the fiber in the form of a roving is impregnated by a resin, and it goes through a die. But in this case, the die is heat because a thermoset polymer is used, and the flow is much lower than for extrusion. And then this material is pulled in order to orientate the fibers. So I think you mentioned this also, bag molding and vacuum molding. In this case, the reinforcement in the form of a mat is deposited on a mold, and a bag or vacuum bag is used, so the vacuum is applied, and the resin is transferred in this mold to impregnate the mat. So 3D printing, you mentioned also, you have done everything, in fact. So it's an additive manufacturing process. You know that it can be used to shape complex forms. There are mainly three techniques, which are fuse deposition modeling, stereolithography, and selective sintering by laser. So I will briefly describe these three techniques. So the fuse deposition modeling works by depositing melt filament material, so it's like extrusion finally, over a built platform layer by layer until completing the part. Now, the stereolithography, so it's a 3D printing technology that builds part by polymerizing. So polymerization is occurring during processing. A liquid photopolymer resin with a UV laser, one layer at a time. So this part is moving here, and progressively with this UV light, the resin is polymerized or cured where it is necessary to obtain this complex shape. And selective laser sintering. So in this case, so this is mainly used with polyamides. A layer of a powder is sprayed, and a laser selectively melt, locally melt the polymer, and then a second layer is added. Again, the laser is selectively melting the polymer and so on. So it is controlled layer by layer. And then the powder is removed in order to recover the solid matter. So, some conclusion. I think so. I am on time. Huh? The processing method depends on the type of polymer matrix, thermoset or thermoplastic. For thermoset polymers, compression molding and transfer molding can be used. For thermoplastic polymer, classical methods are extrusion, injection molding, and rotomolding, but there are many others. This conventional method for preparing molding compound with thermoplastic thermoset polymers are sheet molding compound and bulk molding compound. And specific methods for composite processing that I briefly mentioned at the end of my presentation can be used. And 3D printing is probably an emerging technology. So, thank you very much for your attention.
We can quickly have take some questions. So we will discuss on that. Questions. Yes. Have here. Is any special?
Sir, very informative presentation, sir. Thank you so much. I have one question. Means especially you are explaining various techniques being used for manufacturing of the polymers. You mentioned about the WPC, wood plastic composite.
Yeah.
Where in US this market is growing by 2032 by around 30 billion. Something I saw the
Yes.
graph.
Yeah,
Yeah.
I don't have the-
But then my question is, wood plastic composite contain plastic. So generally, the wood have cellulose more. So when you stick together,
Yeah.
especially with the mica, we say that to get the decorative color, the one challenge what I have seen it, the adhesion will not be good whenever you place another layer onto this wood plastic composite because it's have a thermoplastics.
Yeah.
So the glue generally being used for this won't work for that such kind of an application. So my question is, anything you have an idea or informations, any specific glue that will be very suitable to joining this wood plastic composite with another layer of materials? Maybe
Yeah.
not very specific to this discussion, but
Yeah.
I'll be very happy to
In
know
fact,
about that.
for adding a layer, so you mean a layer of
Layer, yeah.
thermoplastic?
Yeah. On the
Oh.
thermoplastic, generally it's called, impregnated melamine papers that give the decorative colors.
Okay.
Say an example, this assume the WPC. On this, there will be a laminate.
Yeah,
So the
yeah.
laminate has to stick towards to the WPC.
In some cases, it can be hot press,
Okay.
but it depends on the miscibility, in fact, between the two layers. Another option can be welding. Welding, so it consists in locally heating the two layers
Okay.
by the movement of a metallic plate, for example.
Okay.
There are some ultrasound can be used also, and then press the two materials, which are only locally melt.
Okay.
Okay. Another option, but also it depends on the miscibility between the two polymers, is to locally dissolve the two polymers just at the surface and then to assemble in order to promote the diffusion of the macromolecule.
Okay. Okay. Yeah. Thank you so much. Probably the wood composite, generally the thermoplastic content will be very high, right? Generally the polyethylene or
It's
polyethylene.
usually it's polyethylene, yes.
Yeah.
But it can be polypropylene or PVC also.
Okay. Okay. Anyway.
The problem with PVC, I think, is most probably the thermal stability,
With the PVC. Yeah. Okay.
because it can be easily degraded. So one of the drawback is the change in the color, which is, in this case, is not really important because the material is brown.
Okay.
So you cannot see the difference in the color of the matrix.
Yeah. Thank you. I think India also WPC is picking up quite fast.
Yeah.
So I think there is a lot of market is growing around this.
Yes, yes. I don't know if it's good or not. It's more expensive than plain wood. But of course, there is no treatment that you have to apply. But a few years ago, I made a terrace in my house and I use wood. It was wood.
Thank you so much. Thank you.
Sir, are there any natural cross-linker which can enhance the property of biomaterial? Especially you are working in chitosan. So, any natural cross-linker which can enhance the property of biomaterials?
I'm sorry. I was drinking at the same time and I didn't hear you.
Sir, are there any natural cross-linker which can enhance the
Ah,
property?
yes, yes, yes.
Especially you are working in chitosan.
Yes, I don't know. There are some, I think one natural cross-linker, which is broadly used, so I think it depends on the nature of the polymer, of course, is citric acid. Citric acid.
Citric acid.
Yes, I think it's used as a cross-linker. I don't know for which kind of polymer exactly, but
Sir, actually, this citric acid is somewhat weak compared to some synthetic. Are there any strong, some other strong natural cross-linker which you can suggest?
yes, I tell you previously, I'm not chemist, so it means that I cannot synthesize such a cross-linker, but I think that there are many options. I mentioned citric acid because I know it's used and it's easy to find. It's a natural product, but there are probably many other.
Okay, sir.
Okay.
I also worked in chitosan and I also use the citric acid, but it's not get that too much strength to my material. My material is hydrogen.
Yeah, yeah.
I'm working on
In
hydrogen.
fact, I think it depends on the polymer that you are using.
But I tried with genepin.
Genepi, yes.
Yeah, it's somewhat.
You know, genepi is a plant that you can find mainly in the Alps, where I live. No, no, okay. But anyway, you use genepi and it was working or not?
No, I checked the papers.
Ah,
It gives.
you didn't use. Yeah.
No, I'm not worked with since this time. I'm not worked
Okay,
with
okay,
this
okay.
genepin, but I checked with papers. It having somewhat good cross-linking than the citric acid.
I think there are many other natural cross-linker.
I tried with this glutaraldehyde also, sir.
Yes.
But 0.1% is best for the human conception and all. So 0.1%
Yeah.
glutaraldehyde. Up to 0.1% only they suggested for human application.
Okay. Ah, they are angry, probably.